Now it's time to work on the direction of the vectors, which we've talked about before. You'll see the definition, we'll see components with the direction, and then we'll see how to find the direction from the components. Typically, there's a big exception to this, but typically the direction angle will be the angle measured counterclockwise from the positive axis. That's how we've been measuring angles in this class. The big exception is for bearings, except bearings. Bearings are measured from straight north and then around. But we'll cover some of those examples later. So this shows us that the coefficients of I and j could be thought of as the cosine of theta and the sine of theta. So basically, if u is any vector, the component form of u is, remember that this means magnitude here. So it's the scalar multiplication of the magnitude times cosine of theta, sine of theta. If it's in the linear combination form with those unit vectors I and j, we get u cosine theta I, u sine theta j. Here's a really complicated way of talking about how to calculate the angle. I'm going to recommend you write down this part, but you'll see this other kind of stuff in textbooks here. So if v is equal to the magnitude of v times cosine theta I plus magnitude sine theta j, we kind of have to work backwards, where we realize that tangent would be sine over cosine, and then the magnitudes cancel out. And so what that really leads us to realizing is that we have to take the inverse tangent of the coefficients of the I and j, which were the x and y components. So I've kind of simplified all of that. This is how I think of it, and this will work for you as far as I know. But also realize that, you know, this is kind of an important relationship to understand, and so I'll do a couple of examples, and then I'll let you do one. If we're in the linear combination form with the i's and j's, so that means we have 3 units in the I direction, 3 units in the j direction. So there's my vector u. So if this is 3, we want the inverse tangent of 3 over 3, which hopefully you realize is going to be 45. I will do the other one, I'll do C, and I'm going to leave B for you. We're going to take, so if we think of 5 as the delta x and negative 2 as the delta y, we need the inverse tangent of negative 2 over negative 5. And for people who are visual like me, if we start at the origin, that means we went backwards 5 and down 2. And so here's our vector. So we expect to get something over 180 degrees. Now this is important for us to realize, because when I take the inverse tangent of 2 over 5, it doesn't realize that I used a negative number and a negative number. My calculator is going to think I used both positive numbers. So the inverse tangent of 2 divided by 5 is, your calculator says that it's 78.7 degrees. But that's up here in the first quadrant. I want third quadrant, so I actually need to add 180 degrees to this and get 78.7 plus 180. We get 258.7 degrees. So that's a little bit better. That that lines up with where we would expect this to end up with on the axis there. So you're going to do this one. And then working backwards from here, I'll run through this example and I'll give you a separate one. We want the component form of vector v. If we know its magnitude is 6 and its direction is 115. 115 is up here. It's got a magnitude of 6. So my x component here, y component here. My x component will be 6 cosine 115. And my y component will be 6 sine of 115. Once I calculate those, I get my two components as negative 2.5 and 5.4. So v equals those two components. So again, there's a classwork page that's going to go with this, and if you'd like to look into the textbook at what problems these are, here's the homework.